we have a bad case of scale issue, but luckily, I've got just the treatment for it. When writing code, we always assume that memory is linear and contiguous. But how is that possible when hundreds, if not thousands, of processes run on the same machine? Let's consider we have 4 gigs of RAM on our machine. And let's assume that we have a process taking 1 gig at some address here. This can happen if some other process allocated the memory above and freed it upon exiting. Now, imagine we want to start a second process that needs another 2 gigs. We know that we have enough free RAM. After all, 2 plus 2 is 4, minus 1.
That's free, quick maths.
But it's not contiguous. Well, time to download more RAM, I guess. Enter virtual memory. Virtual memory is an abstraction layer that allows the operating system to stitch together physical memory pages to form a seemingly linear block of memory from the process's perspective, as it can only see the virtual addresses. With that, we can use our physical memory to the fullest, and our case above ends with both processes running, and we can even go further by running more processes than our physical memory allows. More on that later. There are a few virtual memory mapping schemes, but in modern OSs, the most widely used one is the PML4, or Page Mapping Level 4. It works by having in CPU register CR3 the physical address of a memory page called the Page Mapping Level 4 table. This address can be anywhere in memory as long as it is page aligned. PML4 tables contain entries, each of which points to a PDP, or Page Directory Pointer table, which in turn points to a page directory entry that points to a page table. The page table finally redirects to a physical page. There are 4 levels of indirection, which is why it's called PML4. Modern CPUs started supporting PML5, which adds another level of indirection. A virtual memory address pointer is an 8 bytes integer. The way virtual memory paging works is by using parts of the virtual address to index into the different page mapping structures. Out of our 64 bits, the top 12 bits are ignored in PML4. Bits 39 to 47, or 9 bits, are used to index into the PML4 table. 9 bits can encode 512 entries, which makes each entry 8 bytes wide. The address read from the PML4 entry is the physical address of the PDP page. We use bits 30 to 38, again 9 bits, to index into the PDP. The address read from it is the physical address of the corresponding PD. We use bits 21 to 29 to index into that to get the page table entry. Bits 12 to 20 are used to get the actual physical page from the virtual address. But we're not done yet. As virtual addresses have a 1 byte granularity, we need to use the remaining bits to index into the page to finally get out the value we're pointing to. One page is 4 kilobytes, and we need 12 bits to encode 4 kilobytes. And we have 12 bits remaining, so that's perfect. This is how we map 4K physical pages. But on x64, pages can also be 2 megabytes, called huge pages, or even 1 gigabyte, called huge TLB pages. This works by choosing not to use all 4 levels of indirection. If we stop the mapping at the page directory pointer level, i.e. the PDP points directly to a physical page instead of a PD, we can use the remaining 30 bits as a page offset, making addressable pages of 1 gigabyte, and giving us a total mappable memory of 512 gigabytes per PDP. If we go one more step down and stop at the page directory level instead, we will have 21 bits to use as page offset, making an addressable page size of 2 megabytes, and giving us a total addressable memory of 1 gigabytes per PD. And since we are using 48 bits for virtual addressing, we can map up to 256 terabytes. Different page sizes exist because of the cost related to traversing the mapping structures to land on a physical page. And the earlier we can stop the traversal, the lesser the cost. A process using 1 gig of memory will need to look up roughly 2 million entries if it's using 4K pages, whereas when using 2 megabytes pages, it only needs to look up north of 4,000 entries. The downside of that is since the OS can only map full pages, using bigger pages can lead to a huge waste of memory space and a lot of fragmentation, which can cripple a system. For that reason, using big pages is often reserved for memory and performance-sensitive applications. Having a virtual mapping unlocks a few cool superpowers for the OS. The most obvious is process address space separation. Processes will have independent address spaces, meaning that two pointers pointing to the same virtual address in two different processes will point to different physical addresses. This effectively shields processes from one another. It's especially crucial for processes handling secrets, like cryptography. But this also means that the OS can map the same physical address to multiple virtual ones. For example, the OS can map the same libraries loaded to some physical memory to multiple address spaces to be used by many processes without duplication. This same trick is used to make cheap ring buffers by mapping a set of physical pages like so that any overflow automatically wraps to the beginning. But the most important superpower is undeniably swapping. The OS, if it needs to, can swap and use physical pages out of memory without killing the process holding them. This can allow the OS to run more processes than the RAM permits, as long as it has another device to back the virtual pages, like a disk. When a process attempts to access a physical page that was swapped out, a page fall is triggered, and the OS swaps the page back into memory. Then the process continues its execution none the wiser. Another variation on swapping is delayed provisioning. If a process allocates a memory page, the OS can choose to only grant the virtual address, without provisioning a physical page to back it, until it gets used. Then the OS fulfills its promise by swapping something else out. If you feel any hyposcalia symptoms, take this skill pill. You'll feel better.